Hey there. So today we're going to be looking at the Putnam 26B2, and I particularly like this question because it requires a certain change in perspective in order to solve it. So you have the question on your screen right now. Okay, so I hope you got a good read on that question, and in the question they have mentioned that only 6 and 7 are the non-squarish integers between 1 and 10. So that basically gives us a good feel for what we mean by squarish. But now I'll give you an example which is kind of misleading. So let's take the example for 12. Okay, so the closest two squares to 12 are 9, which is before 12, and 16, which is after 12. So you may think that, okay, the distance between 12 and 16 is 4, which is a perfect square, and between these two it's 3, which is not a perfect square, but this is a perfect square, so we'll choose this and we'll say that 12 is squarish. But that's not the case because this 16 is not the closest square to 12, it's 9 is the closest square, so that means that the distance from the closest square, which is 9, is 3, and that's not a square, so 12 is not a squarish integer. So we have to keep that in mind, and it's a misconception that may come in your mind if you don't understand the question properly. So I just thought about clearing that up. Okay, so now let's coming to solving the question. So reading the question, the first instinct is that we have an upper bound capital N, and then we are going to every integer between 1 and n, and we are asking it whether are you squarish, and it will tell us yes. If it tells us yes, then we increase the count of Sn by 1, and if it tells us no, then we don't do anything, we move to the next integer. But that is actually a problematic method because it's not really easy to determine when a particular integer is a squarish integer or not. Instead, what we could do is we could go to every perfect square between 1 and n, and we could ask it how many squarish integers do you have. So, but what I mean by that is, let's write some integers. Okay, so I have the numbers from 1 to 16 written out over here. Now let's look at which all are the perfect squares. So that and that. So we have these 4 perfect squares in this interval. So now we'll go to, let's say, the perfect square 4, and we'll ask it how many squarish integers do you have. And what I mean by that is how many squarish integers are related to 4, in the sense that the distance from 4 is a perfect square and the closest square to them is 4. So the closest square to 3 is 4, that to 5 is 4, 6, and then 7, 8 are closest to 9. So we won't count them. So these are the 4 integers which are, 3 integers which are closest to 4. And now how many of them are squarish? 5 is squarish because distance is 1, 4 itself is squarish, and 3 is squarish. So 4 has 3 squarish integers linked to it. Similarly, if we go to 9, now let's ask 9 how many squarish integers it has. It has 10, 11 is not a squarish integer, 12 is not a squarish integer, and 13 is closest to 16. It's not counted with 9. 8 is a squarish integer, but 7 is not a squarish integer, and 6 is linked to 4. So that's why we have 3 squarish integers linked to 9. And similarly, we have 2 squarish integers linked to 1. These two are linked to 1. So this way we can go to every squarish integer, every perfect square, and we'll ask it how many squarish integers do you have. And that way we can add up all the answers that all the perfect squares between 1 and n give us, and that will give us the answer. And then we have an expression for Sn, and then we can take this limit and we'll see what happens later on. So this is the approach, a brief approach. Now we need to figure out the logistics. So let's see what we can do. Okay, so as you would have guessed, we are going to get a summation. So now let's think about what bounds will the summation have and over what exactly are we summing. So what is the parameter of the summation? So let's see. We want to sum all the answers of the perfect squares between 1 and capital N. So what we can do is we take all integers between 1 and root n, and we square them. Because that gives us all the perfect squares between 1 and capital N. So what we can also do is we can take the floor function over here, because root n may or may not be an integer and we want to deal with integers. So we'll take the floor function. So we know that whatever our answer is, it will be a summation as, let's say, some index k equals 1 to floor of root n. So these are the bounds of the summation. Now we need to figure out what answer each perfect square gives us. So for example, as we already saw, 4 had 3 perfect squares linked to it, which are 3, 4 and 5. So 4 gives us the answer 3. Firstly, notice that what we are actually doing is, again I'll write the integers down because it will help me explain it a bit more intuitively. Okay, so what we exactly do is, if we take 4 as an example, firstly we find out what bracket of integers is closest to 4, like in the perfect square sense. So but what I mean by that is 3, the integers from 3 to 6 have the closest integer to closest square, perfect square to them being 4. Similarly, the integers 7 to, let's see, 12 have 9 as the closest perfect square. Similarly, for 16 we have 13 to, let me see, 19, 20, 21, is that right? Yeah, till 20. So these many integers are closest to 16, like, you know what I mean. So now, and of course we have this bracket between 1 and 2. So ideally we should have 0 also, but we'll forget about 0 because the question doesn't include it. So we have all these brackets set up, and then what we do is we find out how many of them are a perfect square distance away. So how many of them are either 4 plus 1 or 4 minus 1, 4 plus 4 or 4 minus 4, although they don't lie in this bracket, so we'll not count that next perfect square. So 3 and 5 are squarish because they are a perfect square distance away from 4. Then for 9 we have 8 and 10, and for 16 we have 15, 17 and, let me see, plus 4, so 20 is also there. So what we basically did is we did 16 plus minus 1, 16 plus minus 4, and then 16 plus minus next square, which is 9. But if we do 9, then we go too far, so we don't want to go too far either. So we have a particular upper bound on what is the maximum square we can add or subtract to 16. And similarly, if we have an integer, perfect square integer k square, then we can have the integers till k plus 1 square, like we'll write them down. Okay, so let's draw them on a number line. So this right here is k plus 1 whole square, this is k square, and this is k minus 1 square, and now we'll figure out what are the brackets for each of these. So k minus 1 square is k square minus 2k minus 1, right? If you just write the expansion and take this common. And similarly, k plus 1 whole square is k square plus 2k plus 1. So you can already intuitively see that if you have, let's say, k square plus k over here and k square plus k plus 1 over here, so somewhere between k square and k plus 1 square, then this side will be belonging to k square and this side will be belonging to k plus 1 square. And you can kind of see why, because from k square plus k plus 1 is a distance k away from k plus 1 whole square, and k square plus k is a distance k away from k square. So both of these are k away from their corresponding squares, and if I try to include this into k squares bracket, then that will that will violate our assumption, and this will not be the k square will not be the closest perfect square to this number. And similarly over here, if we have k square plus k minus 1 and we have k square plus k, then this side will be k squares bracket and this side will be k minus 1 whole squares bracket, because this number is k away from k minus 1 whole square, and similarly this number is k away from k square. Okay, wait, I made a mistake over here. This should be k square minus k, and this should be k square minus k minus 1. So this is the bracket of k square, this side is the bracket of k minus 1 whole square, and this side is the bracket of k plus 1 whole square. So now you can see how many squarish integers will k square produce. Similarly, how many will this guy produce and how many will this guy produce. So we have a bracket of 2k minus 1 integers which lie inside k square's arena or bracket, whatever you want to call it. So now what we'll do is we have to figure out how many of them are squarish. So as we already saw, we are adding and subtracting, right? So you can see over here that 16 has 3 numbers on this side and 4 numbers on this side, and it kind of matches up with our diagram because we can see this side is k minus 1 less and this side is k more. So this is 3 and this is 4. Okay, so now we have to figure out how many squarish integers lie between this bracket. So for that, what we'll do is we'll first look at how many squares are less than k. So the number of squares less than k is floor of root k. So you can think about that, and once you agree with me about this, you can move on. So the number of integers, perfect squares less than k square, and it can be less than or equal to, but it doesn't really matter. We'll see why it doesn't matter later on. So, and similarly, we also want to find how many perfect squares are less than k minus 1, and that's floor of root k minus 1. So that is this blah 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 less than k this is k. Okay, so we have this setup. So that means that the number of squarish integers in this bracket will be floor of root k plus floor of root k minus 1. I'll get rid of this. And this entire thing plus 1. So now you may ask, why do we do the plus 1? Well, that's because we also need to count k square. K square itself is also a perfect square, squarish integer. So we need to include that as well. So this function root of floor k plus root of floor k minus 1 plus 1 is a counting function which counts the number of squarish integers related to k square. So now we have our entire summation set up. This is equal to s of n, except not exactly. There is a slight problem with this, and that is something which happens at the very end. So to explain that problem, let's take the example of n equals 25. So we already have most of those integers till 25 written out, so I'll write the remaining as well. Okay, so now what our function will do is it will find the number of squarish integers related to 1, number of squarish integers related to 4, and so on till number of squarish integers related to 16. Then it will come to 25. But the problem is it will also include the number of squarish integers which are linked to 25 and they are greater than 25. So for example, 26 is a squarish integer which is linked to 25, but it's greater than 25. So our function shouldn't be counting it, but it still will. So that is a problem. But it will turn out that since we are taking the limit as n goes to infinity and then we are dividing it by n to the alpha, that part will be insignificant, and we can prove that using the sandwich theorem. So we'll get that in a minute. So in reality, we shouldn't be putting an equal to sign over here. This should be approximately equals to as n goes to infinity. Okay, so now that we have this set up, now we just need to work out the limit. So I'll get rid of this and I'll be right back. Okay, so this is the expression we want to evaluate, and we also want to find a suitable value for alpha so that this is not 0 and this is also not infinity. So for that, firstly what we'll do is, instead of saying n goes to infinity, I'll say that floor of root n goes to infinity, because you can see that the summation bound is floor of root n, so it's better to have floor of root n going to infinity rather than n going to infinity, and they're the same thing, right? And moreover, we can say that n is approximately equal to floor of root n whole squared, because as n goes to infinity, this approximation gets better and better. If you want to make it more rigorous, what you can do is you divide this by floor of root n to the 2 alpha and multiply it by floor of root n to the 2 alpha. Now notice that n to the alpha is nothing but root n to the 2 alpha, and the limit of this entire thing is the same as this divided by the limit of this thing, and you can see that this part approaches 1 as n goes to infinity, and that means that we can basically cancel these out. They don't matter, and that way we have an expression completely in terms of floor of root n. So how about we give floor of root n a new name? Let's call it small n. So limit as small n goes to infinity of sum as k goes from 1 to small n of whatever that stuff, and then divided by n to the 2 alpha. So this is what we want to evaluate, and you can kind of see that this is looking like an integral in disguise, because you have a summation of something and you're dividing it by n to the power of something. So basically you're adding up many infinitely small pieces, and that is exactly what's integration. So what we'll do is we will try to convert this into an integral. So how do we do that? Let's see. So this is the expression, and now we want to convert this to an integral. So firstly, remember what we need for an integral. We need k over n. So we want this entire thing, the thing which is being summed, to be a function of k over n. We can't have it being a function of something else. So for that, we need to bring this n somehow inside the square root. So how do we do that? Because we can't really take stuff inside a floor function like that. So for that, what we'll do is floor of root or floor of anything, let's say floor of any number x, is between x minus 1, so it can't be equal to x minus 1, right? So this is the bound for floor of x. So can I say, using the sandwich theorem, that this limit is between two limits? So I'll write both of them down. So instead of saying floor of root k, what I'll do is root k minus 1 plus root k minus 1 minus 1 and plus 1 all over n to the 2 alpha. And what I'll also do is I'll write the other limit, k equals 1 to n, and this time instead of taking x minus 1, I'll take x. So root k plus root k minus 1 plus 1 over n to the 2 alpha. So if I prove that these two limits are equal, then by the sandwich theorem, this limit will also be equal to whatever these two limits are equal to, because this is strictly greater than this and less than or equal to this, so it must lie between these. So what we'll do is, it's pretty simple now. We can cancel out this, and then we'll separate out this plus 1 over here. So I'll write it as plus 1 over n to the 2 alpha, but the plus 1 was inside the sum, so this will become n over n to the 2 alpha, and similarly this will become minus n over n to the 2 alpha, and we'll remove that. So basically what I did is I combined all the ones together. Okay, so to convert this expression into an integral, what we need is we need k over n over here instead of k, and similarly this will become k minus 1 over n, and since we divided the top by root n, we also need to divide the bottom by root n, and we also need this entire thing to equal n because this is the dx part. So for that we get an equation that 2 alpha minus half is equal to 1. So alpha is equal to 3/4. And similarly, this is the same expression as this. So we'll get the same value for alpha. Alpha equals to 3/4. And now notice that if I put that over here, we get n over n to the 3 over 2, which as n goes to infinity, this approaches 0. And similarly, this also approaches 0, so that term is useless. And we get an integral over here. So now let's try to figure out what that integral is of. So here we have root k over n, which is our x. And the integral bounds will be from 0 to 1. So we have, where do I write it? Let's write it over here. 0 to 1. And we have root x, and k minus 1 is basically the same as k. We can just change the summation bounds, the integral bounds will remain the same, so we'll get plus root x, another root x, and then this times this entire thing is equal to n, so we have 1 over n, and that is the dx part. So this and this are both equal to this integral right here, so this is our answer. And now let's see what this evaluates to. So using the power rule, this will evaluate to 2/3 plus 2/3, which is 4/3. So 4/3 is the answer for both of these, and since both of these are equal and they are like encompassing this one, so they are on either side of this one, so that means this is also equal to 4/3. So we get that limit as, damn it, I'm out of space. Okay, so we get the final result that limit as capital N goes to infinity of s of n divided by n to the 3/4 is equal to 4/3. So alpha is equal to 3/4 and beta is equal to 4/3, and that is our answer. Thanks for watching.
Turn up. Let's go.